All right, so now that we've taken a look at packing and relaxing with PyRosetta, we're going to think about things that we might want to change in our design protocols. So with relaxing, you got to see the entire structure shift, and if we wanted to restrict, let's say, design or repacking to one CDR loop, we did that. However, we haven't talked about sort of more intricate and sophisticated ways of controlling exactly what gets minimized and where we make these changes. We just need more control over the entire design problem because it's so difficult to sort of approach these problems and have them have experimental success. And so when you think of constraints, what comes to mind? So what's a possible constraint you might want to have while designing a protein? So we don't want to change the orientation at the active site. We want to keep it constant. That could be the case, absolutely. So then do you apply your constraints on the active site or everything but the active site? Just the active site. Can you think of a scenario where you're interested in keeping the active site sort of be the only unconstrained region and everything else keeps conserved? Okay, so maybe you have an existing protein and you want to turn it into a membrane protein, and you might change some regions around to make that possible. Any other example you can think of? So what if we already have a protein that binds to whatever target, but maybe it doesn't have high enough affinity to that target, or maybe it's not specific to just that target. So we might want to change things at the binding site or the active residues such that they do the function more robustly. And so that could be one of the reasons we sort of want to apply constraints and see if we can change things with a lot of control. And so you know about poses, you know about all sorts of functions, you know about scoring, you know about different types of scores, different energy terms. And thinking about constraints and having a more sophisticated way of modifying your pose, what do you think constraints apply, or let me just ask, in terms of the structure versus the sequence, where do you think constraints sort of come into place? Is it more in the sequence space or more in the structure space? Raise your hand if you think constraints are structural. Raise your hand if you think they're sequence-based. All right, let's hear from someone who thinks they're sequence-based. Let's just say that for the active site residues, if you know your residue is already making a bond or an interaction that you'd like to keep conserved, maybe that's the reason to apply constraint, considering the sequence identity. And for those of you who said constraints would be based on the structure, can we hear from someone that we haven't? So in this case, we're thinking, well, maybe there are some structural changes we want to make, either to better fit a sequence or to change the sequence slightly because the structure will allow us to have function. So that makes sense. Let's think about how we can use constraints and what we want to do with PyRosetta specifically. So this is very clear to us, but we're going to specify very clearly exactly how the structure should be restricted. So you can have restriction at the level of residue indices, you can have it at atomic distances, you can have it for certain angles, dihedral, planar, and you can have it, let's say, at side chains, or maybe you're interested in figuring out exactly some structural feature that you're interested in conserving, but there is no score for it. Maybe this has to do with some type of hydrogen bonding that isn't quite possible to detect as accurately with PyRosetta, or maybe you've come up with your own interaction graph that is between a protein and its binding target. And so we're going to think about exactly what you can do at the level of structure to figure out a way to restrict things that they have where they have no energy term associated with them. And so again, an example would be some of the dihedral angles, and you pick a certain region and you're interested in sort of keeping those very well conserved. It could also be some inter-residue distance. You can also have it intra-residue where you're interested in keeping a certain, let's say you're interested in keeping some sidechain conformation, but change other dihedrals around it, and then thus you're changing some of the distances within that neighborhood altogether. And so constraints are just additions or additional rules, and they bias the score function so that whenever you have a new structure that you're sampling, the properties sort of adhere to any constraint specification. And so you're evaluating through different types of structure. And in your evaluation of structural space, you're checking that it meets your requirements. So these requirements are defined in either some constraint file, or you can sort of do it all at once, or it could be based off of a native pose. So you can borrow your constraints from nature. You can borrow it for certain, I guess, scientific challenges like engrafting. You're borrowing a certain part of the protein already, and then the rest is going to be grafted. So constraints do not restrict sampling of structures that might violate these properties. They just make it so that it is very much not preferred to violate the specified properties. So you're still sampling randomly, and your sort of the randomness that is contained in your protocol is much more biased, and you're still minimizing over energy. In our case, it's going to be the ref15 score function, but in doing this, you can sort of change the weight of certain dihedrals. So specifically for a residue, let's say 62 to 103, the dihedral angle's weight contributing to the energy score is so high that they're so heavily punished for moving. So this will allow you to converge your answer towards a structure that you're actually interested in. Before we move on, do you think this would speed up converging to a lower state? So we talked about energy, we talked about local global minima. Do you think this allows you to reach a local minimum faster? Let's do this. Raise your hand if you think yes, it does allow you to reach a local minimum faster. Raise your, raise your hand for nope, it doesn't, and you have to raise your hand to something. Okay, so let's take 5 seconds to think about this. Okay, so what ends up being explored is restricted because of your constraints, and so the space is potentially smaller because of that. And so maybe that saves you some time. And then for those of you who said no, can we hear from someone? Okay, so you're saying since not everything actually adheres to our constraints, it will take a long time to find what does?
Yes.
Okay. We'll come back to that idea. So maybe your constraints are so heavy and applied to maybe so many tricky residues that you can't jump any energy barriers. So maybe you're stuck, and so you can't look for nearby minima. That's possible. It's also possible to have exactly the right constraints, so you're just minimizing onto very close by sort of low energy states. So you could be sampling backbones that are very similar to yours, maybe just slightly better. Maybe just something needed to shift in the backbone, just like tiny minimization. So it will be dependent on the case and exactly what it is that you're constraining. So all answers are correct. So we're going to figure out exactly what we can change about constraints so that whenever we find that our requirement for the structure isn't met, how can we push it to actually get there? So what if we said that, okay, it's okay if they violate it, so not every single conformation you sample is going to adhere to your constraints, but is there a way to make it so? Anybody think of a way you can brute force constraints, and for your sampled conformations that violate constraints, just keep driving that process forward and keep biasing it such that it meets your constraints quite well? All right, well, we'll see the answer anyway, so let's keep going. Constraints are going to have certain qualities to them. So you're going to have to define exactly what it is you're interested in constraining. So it could be a distance, it could be an angle. Also, you're going to have to give it some function that is used to guide and introduce some type of penalty for not agreeing with the constraint. And then, so this third point goes back to possibly a parameter and something that might help us brute force constraints onto a structure even more so is we can change the weights of constraints. So you can have user-defined weights for constraints and adjust them so that it is able to meet your structural requirement. So this will allow you to keep biasing the entire process and the whole search such that it minimizes to a conformation you're interested in. And we're going to also explore different weights in the exercise. So let's talk about how you might want to define a constraint. You're going to take a look at an actual constraint file later on. So just by default, the weight of any defined constraint is going to be 1. You're able to change that. It is relatively arbitrary. So 1 itself doesn't really have any units or anything. It's just the weight. But the higher you go, obviously energy terms associated with your constraint end up becoming very heavy and important to the overall score. And before we move on from this, I'd like to ask you for the CDR loop redesign exercise you were doing. Let's just say that there were constraints on the rest of the backbone and the H1 loop was the only unconstrained region. So given that, let's say you run through the same exact protocol, do you think that the ref 15 score is higher in the native structure or higher in your final repacked minimized structure? So once again, you take native constraints, apply it to the entire turquoise structure, except for the one loop. You let that one loop be relaxed and minimized and repacked in terms of the rotamers. And then the question is, what happens to the ref 15 overall energy score? Is it higher for the native structure or higher for your repacked structure? So maybe it's higher for the native. Anybody think that it's lower for the native? Okay, so it's possible for your unconstrained region to have clashes or other undesirable structural violations that end up ruining the score no matter what. So both ways are possible, and it also depends on what the native structure look like, because some native structures are very, very difficult to minimize, and some are on the easier side. And I'll leave it up to you to think whether antibodies sort of fit the more difficult category or the easier category, and the success rate with Rosetta. But that's more so in the literature than what we're going to discuss. So let's move on and talk about different types of constraints. So you can apply a constraint on an atom pair. So maybe you're interested in adding a score penalty if two residues or two specific atoms belonging to two residues have a deviation on this distance. And so this will be called atom pair constraint, and you can define its weight, and then you would have to identify which atom pair you're doing this for. And so you would need the atom's ID as well as the index at which you can find this atom, and then define the weight and then run with constraints. And then, just as we talked about, so you would have constraints at the level of angles. So this can be whatever angle that you like. You just have to identify which atoms make the angle. And so once you do, you can run a protocol such that whenever you deviate from this exact angle, it will introduce some penalty and be added to your overall energy score. And then same is true for dihedral. And then other types of constraints. So we're not going to go over these necessarily, but you can have, for example, a coordinate-based constraint. So we talked about how you have XYZs for every single atom. And so if you wanted to specify an XYZ at the level of just one atom or a collection of atoms, you would be able to do that. So you want them to stay exactly where they are in 3D and move things around them. So that also relates back to perhaps what you want to do, but you don't necessarily know exactly which dihedral angles allow for that binding mechanism, but you know the XYZ of, let's say, your side chains that is clearly interacting with a metal. So you know the XYZ should not move, but in terms of the angles, in terms of any other atom pair distances, you don't really have too much information. So you might just want to keep a very constrained, a very refined region constrained so that you can keep that interaction to the metal constant. And so in terms of how constraints sort of can be used, or different types of constraints and sort of their overall effect on scoring will depend on different types of functions. So this is sort of based off of how far away you're getting from what was allowed. And you can think of different types of functions that maybe you want to define and have a constraint that sort of follows that. So maybe for your atom pair distance, you want to keep it at, let's say, 2.5 angstroms. And then whenever it moves away, let's say by 150%, there is a lot of penalty for it. But once it makes it over by 200%, you relax the constraint and you sort of don't care about it anymore because they've clearly broken the bond and they should find another atom to make some type of bond with. And so this sort of allows you to define exactly what the overall behavior should be for either when the constraint breaks or when you sort of enter into where the constraint would be applied. And yeah, so what we're going to do is we're going to talk about how you can combine different types of atoms and different types of functions defining what happens with the constraint. And you'll also see that we can create constraint files, which sort of list what exactly is being applied. And you can also combine constraints. So we should probably cover that. You can have multiple constraints. So you could have one that's either at the level of dihedral angles and one that's, let's just say, XYZ coordinates of a specific residue. So you could combine them in that they both need to be they both need to guide your overall protocol a little bit. And then depending on how conflicting or interfering your two constraints are, you might get some interesting effects. So there might be a very high energy sort of cost to having to combine two different constraints, especially if they don't work well together or one of them interferes the other one. So that's definitely possible. And then, yeah, so whenever sort of people work with this, they might be interested in taking the lowest certain number of constraints and then change the behavior such that maybe it's between exploring either two different types of constraints or two different constraint function types, and then their combination, or maybe it's a little bit more relaxed and it has an or connection instead of an and. And so we're going to think about how exactly you can use constraints and whether you want to load it from a constraint file. So it's going to have a .cst extension. And you can also just define it while running your entire collab notebook. So this right here, you already know what this is, but in your initialization, you can pass a constraint flag. And so if you wanted to have a constraint file, in this case, we're looking at a full atom base constraint with hydrogen bonds sort of being the, I guess, basis for a penalty. And based on loading this, you can make certain changes to your pose and see what kinds of structures that you're sampling. And in terms of constraint weights, so this is something that if you actually end up working with constraints and different types of proteins, or maybe just have one protein, but you have to constrain it a lot to get the function that you want in your research project, you'll quickly realize that it's something that you'll have to sort of somewhat feel out. So you'll have to see the results of your overall pipeline to see if the constraint weight is too high or too low. And it takes a while to figure out exactly how to do it without having horrible Ref 15 scores as well. So the delta REU is always going to be quite a bit costly, especially the more constraints you apply. So you'll quickly realize that there is some dependence on size once again. So if you have a very large protein and then you constrain many residues versus you have a smaller protein, it's possible that because especially if it's a native big protein, for that protein, it's going to be hard to sort of figure out how to make any changes that don't interfere or clash with the rest of the protein. Or maybe if it's multi-domain and it's evolved to do this, and nature had so much time to sort of customize exactly what should go where, it'll be difficult to have PyRosetta find a new solution and get to a very nice low energy state. And this is how you would add your constraints. And then for our score function, you know how to define this. And you'll also have this slide if it helps. In terms of creating constraints within a protocol, so instead of loading from a CSV file, let's say that you want to create the constraints, you would add it this way, and you would apply it onto your pose. So you will need to determine exactly what type of constraint is. This one is for a pair of atoms, and you'll also need to select residues. So we don't cover residue selectors explicitly, but I think with the level of expertise that this group has, it is quite easy to use residue selectors by just reading PyRosetta documentation. And you'll be given an example of how to do this. And then, as you can see, atom pair constraint generator has an attribute set max distance. In this case, it is 5. And so that is your cutoff. And after that, you start introducing the penalty. So if you wanted to do a Rosetta-based protocol, there is going to be a different preparation step for it. We're not going to do this. And also, as I sort of hinted to it, it's possible that you have some interaction with a metal that you want to keep constant. So setting up constraints for metals is also possible for Rosetta, but we're not going to directly demonstrate it. This is from some time ago, but essentially Gremlin was developed by Sergei Ovchinnikov in David Baker's lab, and it is used to predict residue-residue contacts. So on the left here, what is this? Anybody know the name of this? We're going to call that a contact map. And what we have here is n by n. So let's say n is the number of total residues we have. And by plotting the distance for all the residues to each other, we can get an idea of their contact. And so what are the types of information we can sort of deduce looking at a contact map? Can you think of anything just related to proteins in general that can be gathered just by looking at the contact? What does the contact map reveal? Once again, it's based off of distance, and in this case, it is based off of evolution, but let's just talk about, instead of evolutionary distance, let's talk about real distance. So let's say I show you an alpha carbon-based histogram instead of what's on the board. So let's just say that this is alpha carbon histogram, and then I have n residues here, n residues here, and then we'll make this really simple. And then let's just say that the distance is going to be just start by doing something like this. So this will take me a second to fill out, but so this is going to be a heat map. And let's say that if it's more filled in versus it's not really filled in, this is going to be high in terms of distance versus low. So this is proximity of alpha carbons. And looking at either this example or that example, what is something you just notice about the figure itself? Just by looking at the squares. Are there any properties that this has? Just that face value. Is there anything noticeable about the pattern? So we have a symmetric contact map. And what does it tell us? Why is it symmetric? So the distance that first residue has to the first residue is the same, right? Okay. What else do we notice? So obviously this is a very mock example, but for every residue, so if we just look at diagonal, every residue's alpha carbon distance to itself should be what? 0, right. And whenever we have, let's say that this is somewhere between, we'll just say it's somewhere between 0 and very high distance. What does it tell us about residue number 3 and residue number 1? Yeah, that they're close to each other. And so from how close two residues are to each other, what's something we can gather from histograms of that nature? So maybe we can see patterns that relate to 3D structure in the contact map. Because the further away their alpha carbons, it might be very much impossible for them to interact in 3D space. And so can you think of why we want to define constraints using either this type of contact map or perhaps one that's based off of coevolutionary signal? What is useful about this being a type of constraint? So maybe you want to preserve the secondary structure. Maybe you want to preserve tertiary disembodied residues. So all of this you would be able to do based on the contact. And let's move on to the discussion. So first of all, you know that we have taken a look at sampling, and we also talked about how the score can be biased with our constraint files, or perhaps you just define a constraint in your protocol. And we also talked about the energy landscape either becoming more limited or it becoming very difficult to jump over an energy barrier. Maybe you're going to struggle finding local minima for introducing a very unlikely constraint. Or maybe the constraint you included, you decided to use is fine, but it's hard to adhere to and still repack the structure. Or whenever you repack, given that constraint, you get some clashes. So all of this will tell you more about what you should change with the constraints, and that maybe your constraints are overpowering the score function and you're changing the entire landscape to the point the score function with its default terms and the term weights don't actually help you search anymore. And so you still have to remain somewhat guided in your overall scheme with some type of pseudo energy so that you're getting closer to the correct answers. And so you need some balance between how high your constraints can weigh versus how much the score function can keep guiding towards that minima. And it is entirely an optimization problem, once again. So here are some resources, and we're going to get started with the constraints lab.